Good evening to everyone. Control. Please give the host control. Okay, so yesterday we have seen the video. Or anyone is having any doubt?
Sir, I have one question, sir. In induction motor, sir.
Yeah, tell me.
Sir, why not in induction motor back EMF is generated, sir?
Induction motor, why not the back EMF is generated? Okay. Induction motor, that is depend upon the induction and it is having a short circuit. So it is also going to have the field. Okay, and that's why the torque is generated. But it is also going to have the back EMF. But back EMF is directly depend upon means your EMF which is going to be generated. That depends upon your induction. Means directly of the supply and there is a losses. If you see the induction motor, I hope that it might have been given you the calculation. And if you see, there are the losses, and due to that, the power which is there, which is going to be transferred from this to that, the rotor, there is a back EMF. But to counteract the back EMF, it is going to increase the current, more current. How to tell about this one? Okay, let me come with the transformer. If you know the transformer, exactly that is what is happening in the motor also. Okay, let me tell you. Then you are going to understand what is exactly it is happening. Here, induction motor. I'll just put here the induction motor. Induction motor. Okay. Wait for 2 minutes. Okay. If you see the transformer, so there is a primary winding and secondary winding. Same here, we are going to have the stator and rotor. Okay. So there is a, like, I'm going to make the transformer first, then you are going to understand this one. So when we are going to give the supply, like this. Okay. So this is the supply. Suppose this is a stator and we are going to give the supply to this one. So there is a current that is going to flow. So this will say initial current or magnetizing current, we can say, because there is going to be magnetizing in this one. So due to that, this current is going to flow initially. I hope everybody know about the magnetizing component and iron loss. There are the two losses are there in this. Okay, IW and I mu. If you have studied, it is going to be parallel to the applied voltage. That is a phasor diagram of this one. It is exactly as we have seen in this transformer and the induction motor. The working principle are same. It is only the rotor which is rotating. That's it. Okay, so it is going to have the two phases in this one. One is going to be your I mu, okay, and one is the IW. So, and this is your flux. So, this is the direction of flux. This is the applied voltage, that is the VP. So, this is the VP here. Okay, so the current which is going to flow, that is this one. This is known as a I naught, initial current. Okay, so initial current is there due to this one is the magnetizing component. This is a sine theta, so the active role is not there in this one, but magnetizing current is there. It is. And which is this is a cos theta. Means the theta what I am taking that is not here, but this one from here to here. So this is the theta naught. So that is the theta naught that is going to come. So IW is the active component, and this is the reactive component. Okay, so there is a iron loss. So this is the iron loss. This is there due to the iron loss. So this VP and this I naught, that is the existence of these two current. Due to that, this is going to exist. Okay, now what happened? There is going to be a flux. So flux is there in the core. Now this flux which is there, now just see here, this flux that is directly depend upon the uh, our applied voltage and the current, magnetic current and the iron loss. So this is the flux. So this is the initial flux, we'll say I naught. So this is the I naught. Now, secondary means we are not connecting, means there is no load. The induction motor is just started, but there is no load is put in this one. We are going to understand in this one. Okay, so if it is not going to be any load, now as soon as you are going to put a load in this, then there is going to be a load current that is going to flow in this one. So this is suppose a load we are going to put and there is a load current that is going to be there, RES. Equivalent diagram of the motor, you can see in that one, it depends upon means the load resistance that depends upon the series. But just I am ignoring to make you understand how this happens. When this current is going to flow, there is going to be a flux of this current also will be there, okay, which is going to produce a back EMF. Remember this, because this is opposite of the main flux. Now suppose the main flux direction was this, okay, this flux, the direction, it is going to be the opposite of this. So it is opposing the main flux. That has to be, Lenz's law says that it has to oppose the main flux. Here how the current is going to be developed? Because of the induction. And the current flow in such a way that it is going to oppose the main flux. So opposite has to be there. Opposition will be there. Okay. So this flux, we will name it phi S, the secondary. Due to the secondary, this flux is there. So this is the load flux. Okay. Now, when there is a secondary flux that is going to come, to counter this one, there is a one more current, means current is going to increase in this, and this current is going to increase, that will say IS prime. If the IS prime, so I will just make a color, I will change the color of this one, IS prime. So this much current that is going to increase due to the load. So there is going to be a current that is going to flow to counteract the phi S. So there is again going to be a flux that is going to be this flux, which is going to be due to the current, additional current that is going to flow. So we will say phi S. Right? Okay. And that is what you mentioned here. This is a voltage that is a ES, and this side is EP. And ES prime, which you saw that certain angle you are showing like this, and this is what you are showing the ES prime. So ES prime is going to be opposite of this is the ES prime that is going to be there. I will come to the phasor diagram again. Sorry, not ES prime, the current which is going to flow, IS, this one, this is the IS, the current which is flowing here, and here the current is going to be the IS prime. So this IS and IS prime is equal. Okay. Now due to this, now there is a two current, there is a I naught and IS prime. So there are two currents are there. Now these two currents, if you see the parallelogram of this one, you will find this is the current that is going to flow due to the load. So IP, main actual primary current. Now this one is equal to basically the IP. These all are the phasored one. So this IP which is there, that is already counteracting the flux which is in opposition. And that's why there is no back EMF. Means basically this and this getting cancelled out. We cannot say cancel out. This is there and that's why this current is going to increase. Okay. Just opposite of this one. and that is the total current that is going to flow, that will be due to the load. Are you getting me?
Yes, sir.
Understood. And that's why there is not going, actually there is a back EMF. This is the back EMF only. Back flux. This flux is there, and due to that there is a back EMF. Means your voltage is going to drop. To maintain a constant voltage, this current is again, it is supplied. It is going to draw this current. So this flux and the voltage which is there, it is going to oppose this. Okay, so opposition is there, back EMF is there, but it is again the flux which is going to increase, and there is a net current in the primary that is going to flow. That's why it looks like there is no back EMF in the induction motor. Hope it is clear. Okay.
Yes, sir. Okay, sir. Thank you, sir.
Okay. So we were here, marine radar and the see this. Okay, first we'll start with Solar's regulation. Solar's regulation. So there is a 9 gigahertz radar, and there is a this one is there, and there is a ARPA. That regulation also we talk, and it is given. First of all, let's see about the 9 gigahertz radar requirement, and it is given in the Solar's chapter 5. Chapter 5. Regulation 19 and para, that is a paragraph 2.3.2, 2.3.3 and 2.5.5. Okay, so this is the para. Now it says that all steps of 300 GT and upwards, 300 GT and upwards, and passenger ships irrespective of size, and in addition, means whatever the requirement is there, other requirements of navigation equipment, because this regulation 19 is a navigational equipment required. Okay, so in this only the requirement of the 9 gigahertz radar is given, and that para I am referring here. Okay, so if you remember this one, this must be more than sufficient for oral. Do not go in the deep. So in addition, that's why this word is coming in addition. In addition, many other things are also there, including the 9 gigahertz radar. Okay, so it says that a 9 gigahertz radar or other means to determine and display the range and bearing of radar transponder and of other surface craft obstructions, buoys, shoreline, and navigational marks to assist in navigation and in collision avoidance. So what it is saying that we supposed to have a 9 gigahertz radar, which is going to determine the and display the range and bearing of radar transponders and of the other surface craft. Now here the word that is coming, the radar transponder. So this is talking about the SART, SART, search and rescue transponder. So this is a radar transponder. This is also known as a radar transponder or radar SART. Okay, this is a radar SART, search and rescue transponder. So in short, we can say radar transponder. So it is talking about this. So this is always going to be 9 gigahertz. There is another type of IMO has already recommended. That is the AIS SAT. We will talk about this when I am going to teach you the GMDSS. Okay, we'll see this one. What is the AIS SAT and how it works? What is the radar SAT and how it works? I will tell you in detail. So it is talking about that. Okay, radar transponder and other surface craft obstructions, buoys, shore lines, and navigational masts to assist the navigation and in collision avoidance. So if you see the display, that is the radar display. Okay. Here, if there is a shore line, so there is a shore line that is going to come, and if some like this marking is also going to come, there is the buoys and all that will come like this. So this is the landmark. There is the landmark. There is the shore line. Any obstruction that is going to come. Okay, and this is known as a target. Generally, we say target in radar terms. It is basically it was before it was used only for the military purpose. So in the military they say target, and that's the word has come target. So in the radar, all the dots that is coming of the ship or anything, that is always we say target only. Okay? So that is how the word has come. You can say object also, there is nothing like that, but generally it is a common word target. Okay. Now, from the center, we have a sweep. Sweep is that is rotating 360 degrees. So this is known as a sweep. Sweep. So this is going to rotate 360 degrees. Okay. And the speed of same of the antenna RPM. That is the scanner. Antenna means scanner. So scanner RPM, what it is there, same it is going to be RPM of this sweep. Now, when it is going to move, this is going to update the target position. Target position. So these two dots are the target position. Now, target position, once we say, that means it is saying the distance between our ship, the center is our ship, this is the on ship position. And from here, how much it is going to have the distance. So first thing, it is going to give a distance. Okay. And second, it is going to give the direction. Direction. Which direction the target is. This target, which direction is there. So direction and distance both are there. In the radar terminology, this distance is known as a range. Remember what is the range? And generally, the range is measured in nautical mile. Okay, so NM we can say nautical mile. It will be in the nautical mile. And direction, that is in the this is known as a bearing. Bearing. Direction means bearing. Okay, and this is in the degree. The degree, how it is going to come? So this degree comes from here. This is considered as 00, and here it is considered at 180 degree, and this is what it is a 90 degree, and this side it is going to be 270 degree. So now if you see from here to here, we can mark it. There will be a marking. So there is going to be the 0 to 90 degree, 90 to 180 marking. Now this is going to coincide with this here, the marking. So that is going to be the degree or direction. So direction we are taking from the 0, 0 position to here. Okay, so always the direction is taken, and that's why it will be degree. Now in the present case, it may be like 80 degrees. So this is going to be the direction. Okay, so direction we are going to get like this. Then there is a range marker and there is going to be a bearing marker in this. So range marker is going to appear like this. One circle that is going to be appearing like this. Okay, so this is known as a virtual range marker. VRM. VRM. Virtual range marker. Okay, so this is the VRM. Then there is a EBL. EBL, it is going to be of different color. Now we are going to align with this like this. So this one, this color, what you are saying, this is the EBL. So that we have to align with the target where it is appearing, that target. And this is a electronic bearing line. So it is going to give the degree. So this reading is going to come. So here at the corner you will find there is a, it will be written bearing and there will be written range, and it is going to give the range and bearing. Okay. So there is a selection range. We can select to different range. As per that, we are going to get bearing and range. Bearing and range not going to change, means the target which is going to appear and display as per the range selection, this range is going to come here. So this is known as a display unit. So display unit is going to have this many information. So there is a display unit. So now this is the what is a SOLAS regulation that says that all ships of the 300 GT and upwards and all passenger ships irrespective of the size that have a 9 gigahertz radar which can detect the radar transponder, that is the SAT, and other surface craft obstruction, buoys, shorelines and navigation must to assist in navigation and in collision avoidance. So there is the mandatory requirement. Okay, now next requirement is given here that an electronic plotting aid or other means to plot electronically range and bearing. Now this word will come again and again, range and bearing. So always this word is going to come. So range and bearing, always it will come, like it is coming there also. Range and bearing of targets to determine collision risk. Now it is saying about the electronic plotting aid. This is not a ARPA. ARPA is different. This is saying about only the electronic plotting aid. Means there has to be some add to the display. So it is going to plot the range and bearing. Now how it is going to plot, just understand this word. Now suppose this is a display and this is a sweep. This sweep is rotating and we have a target here. This is a target. Now what happens, again this sweep is going to come, this target has moved here, again next sweep when it is going to come, it is going to come here. So now it is coming towards the shape. It is going to come towards our shape. If it is going to come towards our shape, that means there is a chances of the collision. There is a chances of the collision. Okay. There is a chances of the collision. So it can collide with us. Now, if it will come to the knowledge of navigator, then precautions can be taken. We can prevent this collision. If we are going to prevent this collision, okay, so there is some floating add is required, which can say, which can update the range and bearing continuously. That means what we are going to do, suppose we are going to we are going to plot this one, automatically it is going to be plot. So automatically how it is going to be plot, so there is going to be we are going to align our range and bearing marker on this and we are going to input. So we are going to give one input. The input means the range and bearing. Range and bearing, both input is given. And suppose this is a electronics floating aid, EPA. Okay, it is a EPA. We are going to give. Again, when the target has changed, we are again going to give this second input now. This was the first input. Then this is a second input. And when it is going to come this third one, we are going to give a third input. So if we give the third input, now after that, if the three inputs are given, now it can determine the coordinate. It can find the coordinate. Coordinate, once we say, that means we are going to find the range and bearing. That is the only coordinate. No? If you see in this one, the range and bearing means present position. So whatever the present position, now the future position of the target, it can say. And if can, that is the coordinate. So if it is going to find the coordinates of the target, that means it can calculate the range and bearing. And this range and bearing is known as a future range and bearing, because it knows now the coordinate, which direction it is going. So this can determine the future position. And it can alert that it may collide with the on ship. How much the distance it is going to cross from here to here. Okay, so this crossing directly it is coming on us, or it is going to go by side. So this future position or the direction of that one, the movement, it can find out, and that is known as a coordinate. That means its course. Coordinate means its course it can find out, so it can avoid the collision. So continuously now we can uh, monitor this one and we can avoid the collision or any type of the alert that is going to be given. So there is a minimum requirement that is there with the 9 gigahertz that is supposed to have a electronic floating aid. It is going to have a electronic floating aid. Okay? I hope it is clear now. Okay. Now next it is saying that all ships of 500 GT and upwards. So 500 GT and upwards, the ships are there. Then they're supposed to have an automatic tracking pad or other means to load automatically range and bearing of targets to determine collision risk. Now here it was a floating edge. Okay, it was a floating edge. So it was not a tracking edge. Automatic tracking is not there. It is plotting, and we are going to input manually this. Once we are going to input, and minimum 3 inputs are required. So it can generate the coordinate, means the movement or the course. So this course of the target can be calculated. Okay, so that is the coordinate, that is the course that can be calculated. So this is a electronic plotting aid. Now what is the automatic tracking aid? Now tracking aid and plotting aid, there is a difference in this one. That now suppose this is a display again, okay, and this is our sweep. So this is a sweep which is going to rotate, and suppose our this is here, this is a heading marker. The heading marker, why I am writing, because this also is there in the display, and this is in the 0, 0 position, means 6 is moving in these directions. Okay. Now what I can do, I can make a sector in this one. So suppose I have given a sector like this. Okay, I have given a sector. So this is the sector I am going to, and I have given a range also. So this is the range. Now range is about suppose 20 nautical miles. This is the 20 nautical miles, and I can give this also, or I cannot give also. Like I have given a 20 nautical mile, and this is the sector I have selected. Now sector I have selected, this is a suppose 40 degree to the left and 40 degrees to the right. Okay, from here. So these we can say minus, and this we can say plus from 0, 0. Wherever our shift is there. Now suppose a target is appearing here, and this is continuously moving. Okay, and as soon as it is going to enter to this sector where I have marked this one, so it will be automatically tracked. It is going to be tracked automatically. So one number is going to be assigned. Now suppose I am assigning a number 11, just like that I have given a number. So I am assigning a number here, 11. Now there is another target that is going to come from here, like this. Okay, and as soon as it is going to come, it is also going to be assigned a number, suppose number 12. This target number 11, target number 12. So the sector and the range, what I have selected, and within that is anything, any target that is going to enter, it is going to be automatically tracked. It is going to be tracked automatically. So this is known as a automatic track. Now, what is the advantage between this automatic track? So any target which is going to come as per our this selection, okay, it is going to be tracked automatically and float automatically. Thereafter, it is going to be float also. So it is going to float automatically the range and bearing. So immediately any target is going to come, will come to know. The operator will come to know, and he can see that there is a collision risk is there or not. So this is talking about the automatic tracking ad. Automatic tracking ad, that is different, means we are giving a sector and this range. And so any target, if it is going to appear, so it will go to the automatic tracking ad, ATA. So these two are the very different one. This one, the input is given physically, manually to the EPA. and ATA is getting automatically because we have selected the sector and the range that we have given. Okay, so like this, automatically if any target is entering to this one, it is going to fly. So this is the difference it is having from the electronic plotting aid and the automatic tracking aid. Okay. Now let's see the next requirement. So this is requirement of the 9 gigahertz and the plotting aid. They are not an ARPA. Again, I am saying this is not an ARPA. ARPA is different. Okay, I will come to that one. What is ARPA? Now there is a requirement of 3 gigahertz radar and ARPA. Now the ARPA is coming. So what is the ARPA? So we will see here. Now it is saying that all shapes of 3000 GT and upwards shall, in addition, again in addition is coming, means whatever it is there, in addition to that, a 3 gigahertz radar or a second 9 gigahertz radar. So you might have seen many times a ship is having two 9 gigahertz radar and some ships are having 9 gigahertz radar also and the 3 gigahertz radar. So this is the SOLAS regulation. Okay. So 3 gigahertz radar is not mandatory. It can be substituted with the second 9 gigahertz radar. So we can have either the 9 gigahertz radar and second or a second 9 gigahertz radar. Rest everything is same. So just I write on dot dot dot. Okay, like this, it is same. Same means you can copy directly this one. Same. Everything is going to be same. Okay, so I will write up to the collision evidence up to here. Up to here it is same. To determine and display, or other means from here to here it is same. Okay. So it is going to be same. So I'm just not writing. And I'm writing after that, means after the avoidance. After the avoidance, I'm writing which are functionally independent. Means both the radar are independent. There is no link between these two radars. So it is totally independent radar. It has to be an independent radar. Okay. So this is the regulation. Now second regulation, it says that a second automatic tracking add or other means, that is same again, to plot automatically range and bearing of other targets to determine collision risk. So up to risks it is same, which are functionally independent. Functionally independent. So it is same. The here whatever it is written, directly you can copy that one or other means from here. Okay, target to determine collision risk and thereafter which are functionally independent. Okay, so this is about the 3 gigahertz radar or a second gigahertz radar. Okay. Now next is all ships of 10,000 GT and upwards shall have, in addition to above, an automatic radar floating head. Now here, if you see automatic radar floating head, this is talking about the ARPA, 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 okay, ARPA, or other means to float automatically range and bearing of at least 20 other targets connected to a device to indicate the speed and distance through the water distance through the water to determine collision risk and simulate a trial maneuver. Okay. Now here the word is coming, that is of ARPA. In ARPA requirement is there only the ships which is having more than the 10,000 GT and upwards. Now the ARPA which is there, that's supposed to be again independent for both the radars. Okay, it has to be independent. Now here it is saying that it's supposed to plot automatically the range and bearing of at least, that is the minimum 20 targets. 20 targets. Okay. What is automatic radar floating aid? Automatic radar floating aid, it is same. If you put these two together, okay, these two together, it becomes the automatic radar floating aid. How it works? Let's tell you about that. Automatic radar floating aid. Now, in this one, we no need to input. What we are going to do, we are just again, if any targets are coming, range and sectors will be given. Now, suppose this is a range and given, and this is the sector I created. Okay. And suppose there are the targets here also. Okay. This one here. And some targets are here. So we can plot this one also. So this I can just putting a window. So this is known as a track window. This is known as a track window. And this is also a track window. So it is tracking already here. Suppose the target number is assigned 1, 2, and something like that. And suppose we are having the another targets that is here, one is here, one is here, one is here, one is here. So these all are having a tracking window. All are going to have their own tracking window, and continuously it is being tracked. Now these windows in this already they have come to the range. whatever it is selected and the sector, within that, this is going to come, and suppose the number is given 11, 12, 13, 14, 15, like that. So continuously it is being updated, and up to the 20 targets, other targets, other target, it is saying other 20 targets, means whatever we are tracking other than that 20 targets more, we is supposed to, it's supposed to track that one automatically. Automatically it's supposed to plot. Now what is the advantage of this plotting? Automatically what we are going to plot, what is the advantage? This is going to calculate again the future position. So closest point of approach. Closest point of approach. This is also known as a CPA. Now, if the two target, I will just tell you about this one. Suppose this is our own ship. Okay, this is our own ship, and this is it is there. One more ship that is going to come from here. Yeah. Like this. Now, the speed is different. Suppose this is running on the 15 knots, and this is going to run on the, suppose, 20 knots. Okay, so here when they are going to cross to each other, okay, so what is going to be the closest? Now suppose after 10 minutes they are going to close, so the ship is going to be here, and from here whatever the distance will be there of this ship, this is known as the closest point of approach. Closest means the closest point. What is the minimum distance between these two ships? That is known as the closest point of approach. So this CPA it is going to give, and second it is going to give the time of CPA. Time of CPA means after 10 minutes, after 15 minutes, after 5 minutes, they are going to close. Now this distance which is going to be crossing to each other, the minimum distance of this one, it should be more than 2 miles. More than minimum, it should be 2 miles. 2 nautical miles we are talking about. Okay, minimum 2 miles. The two shapes in open sea, not in the constrained water. Open sea, it's supposed to move, should cross by 2 nautical miles. Okay, that is the regulation. And what is the time? Otherwise, this one is need to divert this one, okay, or it should cross from the back of this one. So it will be diverting, and little bit this is going to divert or something like that. So at least minimum 2 knots, 2 nautical miles is maintained. So this is the advantage we are going to have with the ARPA. So ARPA is doing exactly this thing, so that the collision that is going to avoid. And second, it is saying that it should have a provision to trial maneuver, which we are going to create the simulate the targets, and we are going to change our direction, our ship's direction, so that we should avoid the collision risk. So this is their simulate the targets for practice. So this practice generally they do on board ship also, and that's why this is a simulate a trial maneuver. So this is the trial maneuver that they practice for that one. That it should always cross at the minimum of 2 nautical miles. Okay. So this is a simulator. It will be having a small simulator, and we should able to simulate the targets, and we can give the speed and direction of that target, so that we can do the practice. So trial maneuver can be done. Hope it is clear about the regulation. Okay. Now we will go on the basic of this one. So marine radar. So it consists of transmitter unit, then second receiver unit, then antenna assembly, then display unit, then synchronizer, then power supply unit. Power supply unit. So this is the basic units you are going to have. Transmitter unit, receiver unit, antenna assembly, display unit, synchronizer, and power supply unit. Okay. Now, working principle is again very simple. Working principle. The name that is given, this working principle, we can say it is a pulse modulated radar. It is a pulse modulated radar. Why it is a pulse modulated radar? We do not transmit continuously. So which is the wave which is going to go out from the radar antenna? It will go in the burst of pulses. Burst of pulses. Okay. So it is not like the continuously we are going to transmit. No, we break it. In the break, we are going to send the transmitting pulse. So this one is known as a, here this one is known as a, this is a transmitting and this is a transmitting time. But this transmitting time is a periodic time. Periodic, remember? Periodic means it is going to happen with a certain period of time. Okay. So this is a periodic time and this is a transmitting again after certain period of time it is going to transmit. This is a width of pulse, transmitting pulse, we can say width of transmitting pulse. Transmitting pulse. Okay, so this one and this one is same. It is a width of the transmitting pulse. Okay. So these widths are going to be in a very small. Okay, it's only like in the point and microseconds it is here. This is generally in the milliseconds from here to here. Okay, so micro and millisecond, the width will be in the microseconds and this is going to be in the milliseconds. Now, when the transmission is stopped at this point, this is the point when it is going to stop the transmission. The reception is going to start. Means between this and this, these two pulses, this is the time. This is a reception time. This is known as a reception time. Means from here to here, up to here, this is a reception time. Reception time. So between two transmitting pulse, it is going to receive. So this is the reception time. Now suppose this pulse, it has gone and it is going to travel it is going to strike the target and again come back. And that's how the range is determined. So range, how we are going to determine the range? This pulse, this is a transmitting pulse. This will travel, okay, and there is a target. Suppose this is a target. This is going to strike this one. Again, there is a reception that is going to come. Receive pulse will come. And it will enter through the antenna to the display unit, and it is going to show a like a pulse here, like this. This one, like this, it is going to show. If it is going to show, there is the target which I have received. That means this one, this particular one, also it has gone, again come back, and this is appearing like this. It is going to appear like this. That means from here to here, how much time it has taken to appear, we can calculate the rate. So this is going to be from here to here range. How we can determine the range? Because we know the speed of the transmitting pulse. Transmitting pulse, that is speed is same light speed, and light is speed. This is the electromagnetic wave. EM waves, we say electromagnetic wave. And the electromagnetic waves, the light is speed, it travels, that is the 3 into 10 to power raised to power 8 meter per second. So this is the speed. So it travels at the light speed. So we know the speed of that one. We know how much time it is taking from going and striking to the target, coming back through the antenna, and in the display it is going to appear. This is the time, we know it. And if we know the time, we can calculate the range or distance. Okay, this is how the range is being calculated. So this is the working principle. That's why we say the working principle is the pulse modulated radar. So it is a pulse. Modulated radar means it is going to repeat. This pulse is going to repeat. And that's why the time of repeat pulse, this is also known as a PRT, pulse reception time. Pulse reception time, PRT. Okay, so this is the width of the transmission pulse, and this is the repeating of the transmission pulse, PRT. So these two words you are going to hear in the radar manual. If you see, these two words will be coming, PRT, pulse repeating time, width of the transmitting pulse. Okay. Okay, you can take a break of 5 minutes, then again we will start.
Oh yeah? Let me see then. Yeah, you definitely failed. Why are you always so mean to me? Let me tell you something. You will never make it. Oh my gosh, sir, you're my favorite actor right now. Do you mind if I get a picture? Thanks. But no. What? Why not? Don't you remember me? I'm Mr. You'll never make it in life.
Excuse me. What time? What time? Time? No, no, no.
भाई क्या देख रहे हो
This is the block diagram of marine radar. So as I have told you, it is going to have that is the 6 units, and here are the 6 units you can see. So first is the transmitter. So there is a unit, there is the transmitter. There is the antenna assembly, that means antenna and the duplexer. There is the antenna assembly. This is the C, that is the receiver unit. Then there is a display unit, trigger unit, that is a synchronizing unit, that is the E, and there is the AF, there is the power unit. Okay, so A, B, C, D, E, F. So this all of that. Trigger unit is also known as a synchronizing unit. Okay. Now, what is a transmitter? It's a very simple, just I give you only for the oral purpose. First of all, the full form of the radar. So the full form is radio detection and ranging. Radio detection and ranging. So this is the full form. It is RA is taken from here. There is the acronym D, A, and R. So it becomes a radar. So this is the acronym of radio detection and ranging. Okay. Now already I have told you this uses EM waves, electromagnetic waves. Now this electromagnetic waves is generated by transmitter unit. Now this transmitter unit which is going to generate these EM waves. Okay, so this will be known as a transmitter. This will be known as a radiated or transmitted EM waves. Transmitter EM waves. Now this will be emitting through the antenna. So we can say radiates in space through scanner or antenna scanner. Now scanner is rotating radius in space through scanner, because scanner is rotating 360 degree. So all around 360 degree it is going to radiate. Okay. So this is about the transmitter. Now EM waves, that is speed, is already I have given you the speed. So it is going to travel at 3 into 10 to power 10 to raise to power 8 meter per second. So this is the speed. So it is going to travel at this speed. Now, when it is going to reach to the target, means when it is reaching to the target, what happens? Now, suppose this is a radar. Okay. This is a radar, and which is going to emit okay, this is a radar, and which is going to emit the pulse. So basically it is making a like this. So this is in the space, means it is going to have the vertical, means it is going to have a height. So this is known as a conical beam width. Almost conical beam width means it is going to have the horizontal plus vertical beam, both the sides. plus and minus means it is going to have the horizontal component also. So we can say like this, and it is, no, I should not make here, it is going to be something like this. Okay, so it is going to have a vertical, and there is going to be a horizontal. Like this. So there is a horizontal and vertical. Both are there. So this is the horizontal and vertical view. Now generally it is used for the surface target, not for the air target. So generally the horizontal beam widths are going to be more. So horizontal beam width, this is the horizontal beam width. It is going to be more angle than the vertical beam width. Vertical beam width is going to have the less angle. Okay. Vertical is going to have the less angle. Generally it is 3 to 5 degree, and vertical beam width is 2 degrees. So there is a degree they are having, horizontal and vertical. You need to see your manual. Okay, whatever it is given, that is there. Now, when it is going to reach to the target. Now, what happens when it is going to reach to the target? So I hope you understood about this. Now let me make again this one. So there is the antenna which is going to rotate 360 degree, and this is going to be rotated by the motor, and we are going to have the motor. So this is the electrical motor. This is driven by the EL. Okay, motor. So electric motor is there, which is going to drive this antenna 360 degrees. So it is rotating, and your beam is rotating all around 360 degrees. Now it is going to radiate. So it is going to radiate. Suppose this is a transmitting pulses, it is going to radiate. This is a beam only. Okay, so I'm making a little peak, so I will just make like this, and slightly it is going to increase. Likewise. Okay. Now here we have a target. Now suppose this is a target. Now what happens? It is going to strike to the target, and after that it is going to be re-radiated. Re-radiated means it is going to re-radiate all around. The same EM wave, it is going to re-radiate all around. It's all around it is going to be radiated like this. And very small portion of this one that is going to come here. That means the power which is transmitted power is there from here, and which has reached to the target again, which is going to come. So this power is going to reduce. So this is a very small power. Very small power. Generally, we measure in the dBm. If you know about the decibel, milli-decibel dBm. Generally, we measure, and this is going to be something like 60 dBm or 50 dBm, likewise. Okay, so this is the power that is going to come. And when we are going to transmit, it is in megawatt, kilowatt. It is going to be in the kilowatt. 25 kilowatt, 30 kilowatt, likewise. So X-band radar, 25 kilowatt. When we transmit, it is a 25 kilowatt, but when it is going to receive, because very small, after covering this distance, a very small power is going to come, and it is in the milliwatt. Okay, it is going to come. So this is going to again enter through the antenna and it is going to enter to the receiver. So this transmitter is a high power, high frequency transmitter. And when it is going to receive a small power that is going to come here, that is a very, very small power. So that power has to be amplified. So received power, so which is receiving is coming, which is received, that is known as a echo. That is known as a echo. Echo is same when you shout and hear your own sound, what you have shouted, that is known as echo. So this is same. It is taken the word, same word, meaning literally meaning same, because it is shouting and same is returning back. Although the returning back power is very, very small, but this is known as the echo. So this echo which is going to come here to the RF amplifier, it will amplify the power of this one. So this is a power amplifier. RF amplifier radio frequency, or this is a high frequency amplifier. So very high frequency amplifier, X band frequency amplifier, and it will be given to the mixture. Now this mixture which is here, this is going to mix local oscillator and the received one. So this is the echo which is there. So now suppose the magnetron which is transmitting the frequency. Now suppose we are going to take 9 gigahertz. That means the echo which is coming here, it is also going to be of 9 gigahertz. We are not taking the Doppler speed and all. So we assume the ship is stationary, target is stationary. So there is no Doppler effect. Okay. In that case, the echo which is going to come, that will be the 9 gigahertz. It is not going to change. Okay. Then the local oscillator, this is going to be tuned to above or below of this magnetron frequency. So suppose it is going to be 9.03 gigahertz. Okay, so this is the gigahertz. That means 30 megahertz above the magnetron frequency. Why we are going to do this one? Because if we are going to have the 9 gigahertz amplifiers, and there will be the 2-3 stages of amplifier, in that case the space required is more and cooling is required more, because we want to amplify the signal. And that's why we are doing the mixing of these two frequencies, that is the received frequency and this frequency. If we are going to mix of this frequency, the net frequency what we are going to get is the 30 megahertz. So this is known as an intermediate frequency. Intermediate means between of this and this. So this is a 30 megahertz. So this echo now has changed to the 30 megahertz echo. So the frequency of the echo is 30 megahertz. Now 30 megahertz, the amplifier required is very, very small. Okay, and that will be amplified. So that is the intermediate frequency amplifier. Now this is a detector. Detector means the signal will be converted into the video signal. So here this is the radio signal. Here the radio signal. That is the echo that will be converted into the video signal. For that we required a detector. So it will change radio signal to video signal. And this will come as a video to the display unit. Display unit is getting two information. One is a heading marker, already I have told you. And there is a antenna information because it has to generate the sweep for presenting the video, that is the target range and bearing, that is the video. So this image or video that has to be represented in the display unit. So which position the antenna is there, and in with that position, if the target reflected wave is coming, so it is going to present the video at that particular path, okay, that particular position. And that's why this antenna information is required. What I am saying here, which you see here, that I try to tell you about this here, like suppose this one, this target. So this target, suppose you will take this target. So now the sweep is rotating 360 degree, and when it is this target is appearing, that means our antenna is facing in this direction only. If some targets are there, suppose here, and here is one image is coming. This we say picture only. The picture of the target which is coming here. Okay, so that means our antenna that time it is facing here. If there is a picture of this target is coming, that means the antenna is facing in this direction. Now these targets are continue to blow. Continue to blow. It doesn't mean that your sweep is always there in this position. No, this is there because there is a coating in the display, and it is going to have the afterglow effect. Afterglow effect. You might be knowing that certainly if your power supply goes, still you can see the pictures in your monitor, okay, or TV. For like 5 seconds, 6 seconds, it is appearing. Okay, so that is known as a afterglow effect. If it is having a layer of coating, it is continue to glow for at least 5 to 10 minutes. And that's why you always feel like that your picture is always there of that target. Okay, so that is due to the afterglow effect. Okay, so this is the use of that one. That means antenna which is radiating, and again it is going to collect back. And when it is collecting back, okay, that is collected back by the antenna and given to the, it is given to the receiver part. Receiver is mixing with the local oscillator frequency, then it gets the intermediate frequency. This radio signal is amplified, given to the detector, and thereafter it is given to the video amplifier, where the target picture is going to be presented, where the antenna is facing in that direction. So that information is required and it is given to display unit. Okay, there is a heading marker, so we'll come to know in the display that which direction the ship is moving. So that is the heading marker that is required. Okay, any doubt to anyone in this? Okay, there is a Harshil Tandel. He is asking me a question that in oral, once they asked me to draw a circuit diagram of duplexer. Okay, duplexer is basically what it is doing. Actually, so much deep they should not ask. First of all, this question is very, very deep. Okay, this duplexer is very different. What it is there in the duplexer, it is going to connect the duplexer. It is a waveguide type things are there in this one. Okay, this is going to be something like this. And Okay, I'm going to make something like this. This is the waveguide. Suppose, and it is splitted, means it is in the two parts. Okay, okay, it is going from here like this. It is splitted, and there is a hole here also, and it is splitted like this. Okay. Suppose, just for example, they are not an accurate one. Just I am making like this. Now what happens? This is your radio frequency which is fine. Okay. And it will be diverted in these directions. So it is going to be diverted in these directions. Uh, Here in these directions, or we can say like this, not like this, but we can say, actually I am not able to make. Okay, I will be making it this way. This is the TR cell. This is a TR cell. And what happens when the target it is going to come, it will not enter and it will not go to this side. This side we are having a receiver. It is a receiver. It will reflect back from here, and thereafter uh, it will enter from here. Like it is coming, then it is going to, from here it is going to reflect back, and it will go like this. It will go to the transmitter. It will go to the antenna, to antenna. And here, this part from here, it is like that, and which is coming from transmitter, from transmitter. So this I'll just draw in the different colors. So this is the wave which will be going. This is a TR cell, transmitting receiving cell. It will not allow to go there. And this energy that will be going from here to the antenna. Why it is not allowing? Because it is going to be in the semi-ionized condition. Semi-ionized condition. You know ionized gas, so you will be knowing about that semi-ionized condition. Now, when it is going to be in the semi-ionized condition, and when the high transmission pulse, the high power one will come, it gets ionized and it blocks the traveling of the EM waves. It blocks. So it is going to be reflected and it will go to the antenna. This is how TR cell works. Okay. Now, where it is placed in the antenna, generally it is placed at the λ/4 distance. Why λ/4 distance is taken? Because it is getting reflected at the λ/4. These all are there, okay? It is related with the wavelength. I just not want to go in the detail. And when the receiver that is coming, received signal, now suppose this is a received signal which is coming. Now because the received signal, there is no transmission that time. So it is a semi-ionized condition, and this is having a very small power. So it will just enter through this and it will go to the receiver. This is how it works. We have a duplexer. I hope this was the question that was asked. Okay. Silpa madam. She is talking. She is seeing from the net, and that is what she is asking. We always search in the net and ask about the duplexer. So there the duplexer, this is how it works. So this is having a TR cell. TR cell means transmitting receiving cell. So this is in the semi-ionized condition. And when the high power is coming, this will get ionized and it will block the EM waves to pass through it. And it will get reflected and it will reflect it towards the antenna. This is how the energy will not go to the receiver. Why it will not go to the receiver? Because it will damage the receiver. Because receiver is made for the very small power to receive. That is how it is working here. Here you can see here this duplexer. Because this energy directly it should go to the antenna and it should not go to the RF amplifier. If it is going, because it is having a very high power, 25 kilowatt already I have told you. So it will damage the receiver. And that's why we put the duplexer. Yeah, this part I have not covered and good question was asked. Okay. Any other thing do you want to ask me? Anything of the radar? Okay. Now we will see the difference between the X and S band radar. X and S band radar. Difference between the X and S band radar. This is the diagram what I have made. This is a wave guide. This is known as a wave guide. The wave which is traveling through this. It may be a coaxial cable also, or it can be made of the coaxial cable, but generally these TR cells and which all are there, this is known as a wave guide. Okay, so this lining what I have put, it is a wave guide. Difference between X band and S band radar. So Sierra band and X-ray band. Now, first of all, you should know there is everything is going to depend. These two parameters are going to change as per their frequency and wavelength. Remember, wavelength and frequency matters. So like X band is 9 gigahertz and S band is 3 gigahertz. So this is how every parameters are going to depend on the frequency of a radar. Okay. So let's see with the item wise. The first item I'm going to take a scanner. Now the frequency which is having a frequency that is very high frequency. Okay, first we will see the frequency itself because everything is going to be depend on the frequency. So this is about 9.2 to 9.5 gigahertz. Okay, that is the X band radar and this is the item. We are discussing X band and here we will be writing about the S band. Okay, X band and S band. So the frequency is going to be 9.2 to 9.5 gigahertz. S band is having 2.9 to 3.1 gigahertz. So just roughly remember 9 gigahertz and 3 gigahertz. 9 gigahertz and 3 gigahertz. This is a band of frequency. Generally, the band of frequency. Now, EM waves are or radio frequency that is divided into many bands, and this is how the bands are known. And that's why it is known as if it is going to operate in the S band, Sierra band. So it is known as a S band radar, and this is working in the X band, and that's why it is known as a X band radar. X band is generally 8 to 12 gigahertz. X band radar. S band, I hope it is 4 to 6 gigahertz. I hope I do not remember. For X band, I remember it is 8 to 12. S band, I hope it is from 4 to 6 gigahertz. Oh, sorry, 2 to 4 gigahertz or 2 to 6 gigahertz, something like that. Okay, that is the S band. It's not to remember. I don't think so. It is required to remember. But why people are asking this all questions? Okay. Then, if you know the frequency, then you know the wavelength. Wavelength is lambda. Lambda is wavelength. Correct? This is a lambda. Okay. So if you know the frequency, you can find out the lambda because we know the speed. So wavelength can we find out? This is about 3 centimeter, and here this is about the 10 centimeter. Now if you see, if your frequency is less, your lambda is going to be more. If frequency is high, your lambda is going to be small. Okay, wavelength. What is the length of the wave in a space? Okay. See, third is your depend upon your range. Range. Now, if you are having a high frequency, then we are going to have a short range. So this depends upon the frequency again. So range is going to be short, and here the range is going to be long. Generally, this is used for the 48 nautical mile in a max. Okay, and this is used for the 96 nautical mile max. So this is how the range is going to change. This is due to the frequency it is changing. Okay, 48 nautical mile, 96 nautical mile. So likewise, the range is also maximum range that can be determined. Okay. Then power output, if the range is less, then power output is also going to be less. Power output means radiation, radiating output, power output. This is the radiating, transmitting power output. Okay. That is radiating from the antenna, that power. This is going to have maximum 25 kilowatt, not more than this is required. It may go more than 30 kilowatt. You need to see the manual. Generally, it is more than 30 kilowatts. Okay. Then come to the scanner, antenna, scanner. If the frequency is less, it is going to require a larger scanner. And if the frequency is very, very small, then it's required a very small antenna, a smaller antenna. So, the antenna size is generally 4 feet, 6 feet, or 8 feet. This is the antenna we have for this one. Whereas for S band, we are going to have 9 or 12 feet antenna. 9 or 12 feet antenna. Why so much larger it is required? Because the frequency is less. That's why this much larger antenna is required. Now RPM. RPM, that is the rotation per minute. Scanner RPM. Scanner rotation. For the short range, high RPM, the short range, it is going to have the high RPM. And if it is a long range, it is going to have the slow RPM. Long range, range selection, we need to select the range. So as per that, RPM is going to vary. So for the long range, it is going to have the slow RPM. Slow RPM. Remember this one? This selection, this will depend upon the selection of range. Selection of range. what is the selection we are going to put? So when we are going to put a maximum 48 nautical miles, suppose whatever the RPM is there, the 96, if I am going to put the maximum, it is going to have a very slow RPM than this. Okay, so maximum RPM, add the maximum range selection. So I will just write here maximum range. It is still is going to have the high RPM. And here the maximum range, when we are going to select a maximum range, it is going to have a slow RPM. Okay. Then 7, that is known as a range resolution. And there is a one word that is also known as a bearing resolution. Now range resolution and bearing resolution, this is the frequency. If it is very high, it is going to be the beta. Here also it is going to be the beta. And if it is a low frequency, it is going to be inferior. Inferior. Here also it is going to be inferior. Inferior than this. What is this range resolution? Resolution and bearing resolution. Now suppose if you are seeing the X band radar and S band radar. Now both are having a, suppose both are operating at the 48 nautical mile, we will say. Okay, both are operating at the 48 nautical mile. And there is a target here. Here, there is a target. These two targets are there very nearby, close to close. But if you see in this one, if you see in this one, it will try to appear as a one big target. Okay, it will try to appear like a one big target. So there is a no separation of a target. Here it is a two target, but it is here it is only one target. So this is a X band. So in the X band, you can see clearly there is a two target separation, separated target. Whereas in the S band, it looks like it is a one target, picture of one target. So this is known as a range resolution and bearing resolution. Okay, range resolution and bearing resolution. 9, that is the start detection. Start detection, it is possible only in this, not applicable for this. So start can be detected only in the 9 GHz radar. Okay. So start detection, yes, and it is not applicable, no. Now sometimes they are asking about the scanner motor. Scanner motor. Generally, the scanner motor in X band is a DC motor. It is not DC motor, sorry. It is a universal motor. Universal motor. Now, universal motor means it is going to work on the DC as well as the AC. Both. It will be working in this one. Okay, that is the universal motor. Your scanner is also very small. Okay, so it's okay. And it is going to give a high torque, of course, high RPM will be there. So generally, it is preferred to use the DC rather than the AC in this way. Now here, because if you are going to use the 12-foot antenna, in that case, you required a 3-phase motor. Okay, so generally here we are going to have a 3-phase AC motor. And sometimes you will find some radar models, they are having a synchronous motor. Synchronous motor. Now, if the synchronous motor is there, what is the advantage? That there will be no effect of no effect of wind, speed, and direction. Now, suppose there is a very high speed wind is there. Okay, and our antenna is rotating, then the load is going to increase and decrease. If load increases and decreases, so your RPM is going to change. RPM changes. And if the RPM is going to change, this is not good. So RPM should not change. It should be always a constant speed. So constant speed is given only by the synchronous motor. No other motors is going to give a constant speed. And that's the reason the synchronous motor is preferred. If your scanner is very large, then there should not be any effect of the wind speed and direction. If the wind is blowing very high speed and direction means speed only, we are not good. Direction means what? Because it is rotating in 360 degrees. So we will not talk about the direction. But if the wind speed is very high, then the load is going to continuously, it is going to change, it is going to increase or decrease. And due to that, your RPM is going to change. And if we required a constant speed, we required constant speed. In that case, we prefer a synchronous motor because in a load change also it will give always a constant speed. That is the characteristics of the synchronous motor. Okay, hope it is clear. Now, any doubt up to here to anyone? Okay, tomorrow I will tell you about the performance monitor. What is performance monitor? Then I will tell you the radar magnetron replacement procedure. This is the two that is always being asked. Okay, then I will tell you a little bit about the ARPA also. Okay, so that tomorrow we will see about this. Okay, any doubt up to here to anyone? Okay, okay then. Thank you very much. Good night to everyone.